So, Assalamualaikum warahmatullahi ta'ala wabarakatuh. So, this is the second part of our video. So, models of traffic flow. With the basic relationship among traffic flow, speed, and density formalized, attention can now be directed toward a more microscopic view of traffic flow. That is, instead of simply modeling the number of vehicles passing a specified point on a highway in some time interval, there is considerable analytic value in modeling the time between the arrivals of successive vehicles. So the most simplistic approach to vehicle arrival modeling is to assume that all vehicles are equally or uniformly spaced. This results in what is termed or deterministic uniformal arrival pattern, under the assumption in that the traffic flow is 360 vehicles over h. So the number of vehicles arriving in any 5 minutes time in interval is 30, and the headway between all vehicles is 10 seconds, because h will equal to 3,600 over q. So, however, actual observations show that such an uniformity of traffic flow is not always realistic, because some 5-minute intervals are likely to have more or less traffic flow that other 5-minute interval. Thus, a representation of vehicle arrival that goes beyond the deterministic uniform assumption is often warranted. So, Poisson model. Model that account for the non-uniformity of flow are derived by assuming that the pattern of vehicles arrival at a specified point corresponds to some random process. The problem then becomes one or selecting probability distribution that is a reasonable representation of observed traffic arrival pattern. An example such as distribution is the Poisson distribution on 8. So, example. So, an observer counts 360 vehicles over h at a specific highway location, assuming that the arrival of vehicles at this highway location is Poisson distributed. So, estimate the probabilities of having 0, 1, 2, 3, 4, and 5 or more vehicles arriving over a 20 seconds time interval. So, this is the solution. So, the arrival rate is 360 vehicles over h, or 0.1 vehicles per second. Using this in equation 5.23 with t is equals to 20 seconds, the probability of having exactly 0, 1, 2, 3, 4, and 5, 1, 2, 3, 4, and vehicles arrive are. So, the solution is P of 0 equals to 0.1 times 20 of 0 squared. E is E squared, I squared of 0, negative 0.1 times 20 over 0 punctuation is equals to 0.135. So, same process lang hanggang sa P of 4. Then, for 5 or more vehicles, P of n less than or equal to 5 is equals to 1 minus P of n greater than 5. So, equals to 1 minus 0.135 minus 0.271 minus 0.271 minus 0.180 minus 0.90 is equals to 0.053. This is the histogram of this probability shown in 5.5. So, this is the histogram. Next is the assumption of Poisson vehicle. So, example 5.6. So, consider the traffic situation in example 5.4, 360 vehicles over h. Again, assume the vehicle arrives are Poisson distributed. What is the probability that the gap between successive vehicles will less than 8 seconds? And what is the probability the gap between successive vehicles will be between 8 and 10 seconds? So, this is the solution. So, by the definition, P of h is greater than t is equals 1 minus P of h is less than or equal to 1, this expression gives the probability that the gap will be less than 8 seconds as P of h is greater than 8 is equals 1 minus e squared of negative 360 times 8 over 3600 is equals to 1 minus 0.449 is equals to 0.551. So, to determine the probability that the gap will be between 8 and 10 seconds, compute the probability that the gap will be greater than or equal to 10 seconds. So, P of h is greater than 8 equals 1 minus e squared of negative 360 times 10 over 3600 is equals to 0.368. So, the probability that the gap will be between 8 and 10 seconds is 0.081. Then the next is makikita nyo dito yung graph. Next is the limitation of Poisson model. So, empirical observation have shown that the assumption of Poisson distributed traffic arrivals is most realistic in lightly congested traffic condition. As a traffic flow become heavily congested or when traffic signal cause cyclical traffic stream distributants, other distribution of traffic flow become more appropriate. So, the primary limitation of the Poisson model of vehicles arrival is the constraint imposed by the Poisson distribution that the mean of period observation equals the variance. So, for the example, the mean of period observed traffic in example 5.5 is 6.733 and the corresponding variance is 7.210. Because these two values are close, the Poisson model was appropriate for this example. If the variance is significantly greater than the mean, the data are said to be over-dispersed. So, and if the variance is significantly less than the mean, the data are said to be under-dispersed. In either case, the Poisson distribution is no longer appropriate and another distribution should be. Such distribution are discussed in detail in more specialized sources. So, queuing theory and traffic flow analysis. So, the formation of traffic queues during congested period is a source of considerable time delay and result in a loss of highway performance. Under extreme condition, queuing delay can account for 90% or more motorists' total trip travel time. Given this, it is essential in traffic analysis that one develop a clear understanding of the characteristic of queue formation and dissipation along with mathematical formulation that can predict queuing related elements. As is well known, the problem of queuing is not unique to traffic analysis. Many non-transportation fields such as design and operation of individual plants, retail, store, service-oriented industry, and computer network must also give serious consideration to the problem of queuing. So, next is the impact that queues have on performance and productivity in manufacturing, retailing, and other fields has led to numerous theories of queuing behavior, the process by which queues dissipate. As will be shown, the models of traffic presented earlier, uniform deterministic arrivals and Poisson arrivals, will form basis for studying traveling queues with the more general context of queuing